Hello everyone. So this is a new beginning. Now we are going to start a new unit in which I will teach you guys some mechanical property of solids, then some mechanical property of fluids, followed by surface tension, then oscillations, and then the most important one, which is waves. All these units have a good representation in your NEET examination. All of them are theoretical. So when I am teaching theory, pay more attention. Theoretical questions come from these particular section, and if the numerical comes, numericals are very straightforward and easy to score. So without wasting time, let's start the first part, which is the some mechanical properties of solids. So in some mechanical properties of solids, we will talk about stresses and strains. There are three types of stresses, and corresponding to them there are three types of strains. So the first one we are going to discuss about is called longitudinal stress, and the strain produced by it called longitudinal strain. If you have a rod and forces are applied at the two ends of the rod such that the force acts perpendicular to the cross-sectional area. As you can see in this diagram, this force is trying to elongate the rod. Such a force which tries to elongate the object creates a stress which is called the tensile stress. It tries to increase the length. Now we define a quantity called stress. Stress is nothing but the force acting per unit area. Now somebody might say stress is just like pressure, force per unit area. No beta, stress is a tensor quantity while pressure is a scalar quantity. So keep in mind the formula looks the same, but stress is a tensor quantity. It's a different quantity. It is defined for solids. So now here you have got an object and forces are applied at the two ends such that the forces are perpendicular to the cross-sectional area. Now this force tries to do what? So this force tries to increase the length. Okay, so if the original length is L, after application of force the length will increase, and let's say the length becomes L plus delta L. There can be one more case when the forces are trying to compress the rod. If the forces are acting perpendicular to the cross-sectional area and the forces are trying to compress the rod, then such forces create a stress which is called compressive stress. So when they try to elongate, it's called tensile stress. When they try to compress, it's called compressive stress. What does the compressive stress do? So compressive stress will decrease the length of this rod. So after the action of this compressive stress, the length will decrease, and let's say the length becomes less than L, equals to L minus delta L. Now all three types of stress, which three types? Longitudinal, shear, volumetric, produce three types of strains. So here the type of strain produced is called longitudinal strain. How do we define longitudinal strain? Longitudinal strain is nothing but change in length upon original length. While teaching you some part of thermal expansion, I use the same formula. There I define what is this delta L. So this is change in length. No beta, you should say this delta L is the change in length because of the application of force. The change in length can even take place due to heating, as in the case of linear expansion. But when we are defining strain, it is the change in length produced due to the application of forces. Okay? Now, so we have learned what is longitudinal stress. We have learned what is longitudinal strain. Let's move on to the shear stress and shear strain. So similarly, there is something called shear stress and shear strain. So what is shear stress? When you take a deck of card and you apply a horizontal force on the top card, the shape of the deck of card changes from being stacked vertically up to some parallelogram shape, right? When you apply the force on the top layer, this means that the card move over each other layer by layer. Such a force which try to move the object layer over layer over layer is called shear stress. Now, how do we define shear stress? To understand it, visualize a cuboid of length L, width B and height H. Let's say the lower surface of this cuboid is fixed, and on the top surface we have applied a force F. Now what will be the shear stress produced by this force? Again the same type of definition, force per unit area. But which area we should consider here? The area that tries to move. When you apply the force on the top layer keeping the lowest layer fixed, this area starts to shift one over another. So we define shear stress as the force upon the area of the layer that shifts. So here the area of the layer that will move layer over layer, that area has to be considered, and that area is nothing but L times B. Notice that here the force acts in the plane of the area. In case of longitudinal, the force acted perpendicular to the plane of the area. In case of shear, the force acts along the plane of the area. Shear stress produced by this force will be written as the force divided by the area which is trying to move layer over layer, and that area is nothing but LB. So now we know that we have understood something called shear stress. Now we will talk about something called shear strain. So if you apply some force on the top layer, yes, the top layer shifts with respect to lower layer, yes. Let's say the top layer shifts by distance x with respect to the lowest layer, as the lowest layer is fixed. We define the shear strain to be equal to the distance moved by top layer with respect to the lowest layer upon the separation between them, which is h. So we define the shear strain to be equals to x by h. You can see in this right angle triangle, this quantity x by h also have to be equal to tan theta, tan of this angle theta, because we are getting a right angle triangle. So shear strain will be equals to x by h, and that will be equal to tan theta. For small value of theta, we can approximate sine theta to theta as well as tan theta to theta. So for small value of theta, sine theta can be approximated to tan theta, and this can be approximated to theta. But when you do this, you have to be really cautious that you should take theta in radian. You must take theta in radian. So here in place of tan theta, you can even write theta. So we will say for small value of theta, we will say the shear strain equals to x by h nearly equal to theta. Better remember that here theta should be taken in radian. So we have talked about longitudinal stress, longitudinal strain. We have talked about shear stress, shear strain. So what is the difference between longitudinal and shear? In case of longitudinal, the force acted perpendicular to the cross-sectional area. In case of shear, the force acts parallel to this same layer. So it tries to move it layer by layer. Okay, sir. Now let's talk about the third type of stress and strain before we delve further into it. So now let's talk about volumetric stress and volumetric strain. What is the meaning of volumetric stress? Visualize this, that you have a container. Okay, the container is filled with a fluid, and there is a piston on the top of fluid. And within this fluid, you have placed an object. If we increase the pressure in the fluid, how will you increase? Just by placing a mass on the top of piston. So when we place a mass on the top of this piston, we know that here the pressure will increase by an amount equals to the excess force acting, which is mg, due to the weight of the block, divided by the cross-sectional area of this piston. So the pressure will increase by an amount mg by a. Due to this increased pressure, the force acting on the body from all sides due to the fluid will now be greater than before. Since the force acting on the body from all sides will now be greater than before, the body will shrink, and hence the volume of this body will decrease. So the increase in pressure from all the sides decreases the volume of the body. To the contrary, if let's say already this block was placed and now you have removed the block, so the pressure of the fluid in the container will decrease. As the surrounding pressure will decrease, the surrounding compressive forces will decrease, so this body will expand and hence its volume will increase, and this creates volumetric strain. So let's understand this one more time. So let's say there is a body which has got a volume V. If the surrounding pressure increases, then there are more forces from all the side on this body, and hence the volume of this body will decrease, and let's say the volume of this body decreases from V and become V minus delta V. The shape is not at all changing, it's just that the body has shrunk a little. To the contrary, if the surrounding pressure decreases, then the body swells up, the volume will increase, and you will say the new volume of the body has to be more than before. So let's say the new volume will be V plus delta V. Now we say that the volumetric strain produced is nothing but the change in volume upon the original volume. Volumetric strain is nothing but change in volume upon the original volume. And the volumetric stress is nothing but the change in pressure. Change in pressure of the surrounding creates a volumetric stress which changes the volume of this body, and due to the change in the volume of the body we say that a strain is created, and this strain is called volumetric strain. So now let's move on and talk about Hooke's law. What is Hooke's law? A simple law. It says that for small value of strain, the stress is directly proportional to strain. For small value of strain, the stress is directly proportional to strain. You can't have large strain. You should have only small strain. So for small value of strain, the stress is directly proportional to strain. Sir, which stress is proportional to which strain? You have taught us three types of stress, and there are three types of strain. The idea is for small value of stress or strain, the stress is directly proportional to strain. Longitudinal stress is directly proportional to longitudinal strain. Shear stress is directly proportional to shear strain, and volumetric stress is directly proportional to volumetric strain. So we say that longitudinal stress is directly proportional to longitudinal strain. Every time in this world a physicist find a proportionality, what do? They add up a proportionality constant. So they have added a proportionality constant in this case, and that proportionality constant is called Young's modulus. So longitudinal stress equals to some proportionality constant into longitudinal strain, and this proportionality constant here is represented by a symbol y, and it is called Young's modulus. So we say y is Young's modulus, and Young's modulus is nothing but longitudinal stress upon longitudinal strain. Now bachcho, tell me, Young's modulus depends upon what? Longitudinal stress, longitudinal strain, both or none? Young's modulus depends upon longitudinal stress, longitudinal strain, on both of them or on none of them. It's a proportionality constant. It is independent of both longitudinal stress as well as longitudinal strain. On doubling the longitudinal stress, the longitudinal strain also become double, and the ratio remains the same. On tripling the longitudinal stress, if you apply 3 times the force, the longitudinal strain will triple, the change in length will triple. So the strain will triple, but the Young's modulus will remain the same. So Young's modulus of a material is independent of the longitudinal stress as well as of the longitudinal strain. It's a proportionality constant. Now moving on. Similarly, just the way we have defined Young's modulus for longitudinal stress and longitudinal strain, we have defined another proportionality constant called the modulus of rigidity or the shear modulus. Modulus of rigidity or the shear modulus for shear stress and shear strain. So we say the modulus of rigidity or shear modulus equals to shear stress upon shear strain. Similarly, one more proportionality, we know that volumetric stress is also directly proportional to volumetric strain. So we have defined one more constant which is called the bulk modulus, or the bulk modulus, which is represented as beta, equals to the volumetric stress upon volumetric strain. Actually, this is not the right definition. There is a minus sign, but I will talk about this minus sign when we are talking about bulk modulus in detail. So let's now treat each of the modulus in detail. First of all, I will start with the Young's modulus. Let's talk about Young's modulus. So if you have a rod and the rod has a length L, the cross-sectional area is A, and we apply a force F at one of the end of the rod, we will say that the Young's modulus has to be equals to longitudinal stress upon longitudinal strain. Yes. If this rod has a cross-sectional area A, and original length before the application of force was L, and after the application of this force, which is trying to increase the length, is L plus delta L. So we will say the longitudinal stress on this rod will be nothing but force upon area, and the longitudinal strain on this rod has to be equal to the change in length upon length. Now we can rewrite this particular equation as F equals to YA delta L by L. And I tell students to remember this particular way, F equals to YA delta L by L. Why? It will be useful later. But how we got it? We know that Young's modulus equals to force upon area, the longitudinal stress upon delta L by L, the longitudinal strain. Bring this longitudinal strain to the right hand side. So you get Y into delta L by L equals to force acting per unit area, which is the longitudinal stress. Also move this area here. So you will get F equals to YA delta L by L. Sir, why do you emphasize on remembering the force in this way, F equals to YA delta L by L? Because there are benefits to it. We have learned that for a spring, if we apply a force F, then the force is directly proportional to the deformation in spring, and then we add up a proportionality constant and write F equals to Kx. Here also notice that the force is directly proportional to the deformation in the length of the rod. The force is directly proportional to delta L, and there is a proportionality constant. Proportionality constant is YA by L. So we say that F equals to YA by L into delta L. Treat this part YA by L as your proportionality constant, and you can write F equals to K into delta L. Now whatever you have learned in spring, that can be applied here as well. First thing, the proportionality constant for a spring is inversely proportional to the length of spring. If the length of spring becomes double, the proportionality constant becomes half. If the length of spring becomes triple, the proportionality constant becomes 1/3, right? Notice here also the proportionality constant is inversely proportional to length. K, which is YA by L, is inversely proportional to length. So greater the length of the rod, the less will be the value of K, proportionality constant. Okay. Next thing, bachcho. For springs in series, we use 1 upon K equivalent equals to 1 by K1 plus 1 by K2. Same thing can be used for two rods in series. So it is useful to remember this spring constant is YA by L. Comparison. For springs in parallel, we know that the spring constant comes out to be, K equivalent comes out to be K1 plus K2. The same thing can be used here as well for two rods connected in parallel. Okay, you will say the equivalent value of YA by L equivalent equals to YA1 by L1 plus Y2A2 by L2. Okay, so you can use the parallel combination of springs as well here. Now, bachcho, there is one thing you need to remember. What happens to the Young's modulus of a material when you heat it? Sir, Young's modulus equals to longitudinal stress upon longitudinal strain. If I ask you, if I heat this pen, then elongating this pen will become easier or difficult. So this pen is made up of plastic. So if you heat it up, elongating it becomes easier. So if you heat up an object, then for the same value of stress, you get more strain. If you heat up an object, here chemistry is involved. What I'm saying, it doesn't work for 100% of object, but it works for many of them, right? So if you heat up an object, then for same value of stress, same force per unit area, the strain will be more. It elongates more. So the strain increases. So the stress is same, numerator is same, the denominator increases. It means that the Young's modulus decreases. So remember that Young's modulus is a property of substance, no doubt. But when you heat up a substance for same value of stress, you start getting more strain. This means that on heating an object, its Young's modulus decreases. So on heating a substance, the Young's modulus of the substance decreases. Again, I am saying Young's modulus of a substance is independent of the stress and strain, but it do depend upon temperature. And on heating up objects, usually, because the chemistry is involved, usually the Young's modulus decreases. Let's move on. So now let's see a question. So the question goes like, if a wire of mass m and length L having Young's modulus y is suspended under its own weight, determine the elongation in the wire. How much elongation will take place in this wire if it has a Young's modulus y and a cross-sectional area A? At the lowest end of this wire, the tension will be 0. At the highest end of this wire, the tension will be equal to the weight of the wire, and that will be equals to mg. Moving from the bottom of the wire till the top, the force will continuously increase. We have just learned a formula, F equals to YA delta L by L. This formula can be used when the force is constant, and those type of questions are really easy. That's why I'm not wasting your time discussing them here. I'm taking up the case of variable forces. So the force keeps on changing as we move from the lowest end to the top end. Then sir, how to use this particular formula? A smart chap might say, sir, see, at the lowest point, the tension is 0, so the force is 0. At the highest point, the tension is due to the weight of the whole wire, so the tension will be equals to mg. So I can use the formula F equals to YA delta L by L. Just that in place of F, I will take the average force. At the lowest end, the force is 0. At the highest end, the force is mg. So I will take the average force, which will be 0 plus mg by 2. And this will be equals to YA delta L by L. And from here, I can find the elongation. If you did this, you will be %% correct, and this is what I want to teach you here. That if the force changes linearly, then you can take the average value of the force acting on the two ends. And it works. So, but first, let's derive it so that you will have faith on it. So you will say, at the lowest end, at the bottom, the tension is 0. And at the highest point, the tension is mg. So as we move from the bottom to the top, the tension keeps on increasing. So the tension in the wire increases as we move from the bottom of the wire where the tension is 0 to the top of the wire where the tension is mg. Now going from the bottom to the top, the tension increases. Yes. What will be the tension at a random distance x above the lower end? So sir, the tension at a random distance x above the lower end will be due to the weight of wire of length x. The whole wire has a mass m. Yes sir. The whole wire has a length L. Yes sir. So what will be the mass of this length x? Sir, we can find the mass per unit length to be m by L multiplied by the length of this part x. So that will be the mass up to length x. So the mass will be m into x by L. So the tension at this point will be equals to the mass suspended below it, which is m into x by L multiplied by g. So the force at a distance x from the lower end is given by mg x by L. Once you have established this force, game over. You will say, now if I consider an infinitely small length of this wire having an infinitely small length dx, then for this infinitely small length dx, I can assume the force to be constant equals to mg x by L. In this infinitely small length, if I assume a further infinitely small elongation d delta, then I can say the force, which is mg x by L, equals to ya d delta by dx. So what is d delta? The infinitely small elongation in an infinitely small length dx. Now bachcho, you can bring this dx to the left hand side up. So you will get mg by L into x dx equals to ya d delta. To find the total elongation, integrate both the sides. On the left hand side, you have to integrate x from the lowest value 0 to the highest value L. So integrate x from 0 to L. And on the right hand side, integrate d delta. What is d delta? The infinitely small elongation in an infinitely small length dx from 0 to delta L. So as we know that F equals to ya delta L by L, using the same thing, in place of F writing mgx by L, and in place of delta L writing d delta. So we get this expression mg by L into integral x dx from 0 to L equals to ya times integral d delta from 0 to delta L. Now the integration part is easy. Integration of x dx gives you what? X square by 2, lower limit 0, upper limit L. Integration of d delta gives you what? Delta, lower limit 0, upper limit delta L. So on the left hand side, after integrating, you will get mg by L, which is a constant outside. Integration of x dx gives you x square by 2, lower limit 0, upper limit L. And on the right hand side, on integration of d delta, you will get delta, the elongation, the lower limit 0, upper limit delta L. So on the right hand side, integration of d delta 0 to delta L gives you simply delta L. So equals to ya delta L. Now beta, once you substitute the limit here from 0 to L, on the left hand side you will be left with mg L square by 2, and there is one L in denominator already, equals to ya delta L. So cancel out 1L with 1L. So what you get is mgl by, bring this ya on the left hand side, 2ya equals to delta L. So you can write mgl by 2ya equals to delta L. Or you can keep the mg by 2 to the left hand side and bring this ya on the right hand side and L also on the right hand side. So you will get mg by 2 equals to ya delta L by L. So that's what I was saying in the very beginning before we did this integration. Simply take the average. So take the average of what? The force. At the lowest point, the tension is 0. At the highest point, the tension is mg. In the formula, F equals to ya delta L by L. Take the average force, 0 plus mg by 2. Simply substitute mg by 2. You will get the same result. So let's practice more question how to utilize this particular method. Let's say we have this wire. The wire has a mass m, Young's modulus y, length L. And at the bottom of this wire, we have suspended a mass capital M. Now, at the bottom of the wire, you can't take tension as 0. It will be due to the weight suspended below it. So at the bottom now, the tension will be mg. At the top, the tension will be due to the entire weight suspended below it, which is m plus m into g. So determine what will be the elongation in this wire. That is the mission. So you will say at the lowest point tension is capital Mg. At the highest point tension is capital M plus small m into g. Going from the bottom till the top of the wire, the tension keeps on increasing. So sir, what force to take? The average of the two. The average of the one at the lowest point and the one at the highest point. And then use the formula F equals to ya delta L by L, substituting here the average force. So you will say from F equals to ya delta L by L. In place of F, substitute the tension at lowest point capital Mg plus the tension at highest point capital M plus small m into g divided by 2, and this equals to ya delta L by L. So now here capital Mg plus small mg by 2, so you get 2 times capital Mg plus small mg by 2, which is same as capital Mg plus small mg by 2 equals to ya delta L by L. And from here you can find elongation, moving this L up and ya in the denominator. So this method can be used here as well. Now let's see next example. Let's say you have a rod of length L, cross-sectional area A, Young's modulus y, and on the two end you can see there are two forces. Both the forces are trying to increase the length, right? Both the forces are trying to elongate it. So how will you write the elongation in this particular rod? So you will say, sir, both the forces are trying to elongate the rod. Yes. So I know that F equals to ya delta L by L, but sir, here the force is not at all constant. The force is changing. On the left hand, force is F2. On the right hand, force is F1. So what to do? Take the average, as both the forces are trying to elongate. You will simply write F1 plus F2 by 2 equals to ya delta L by L. So what if one of the force is trying to decrease the length? As in this diagram, you can see F1 is trying to increase the length while F2 is trying to decrease the length. Then sir, what to do? But I still take the average. But remember that one of the force is trying to decrease the length. So I will write F1 minus F2 by 2. F1 minus F2 by 2, as one of the force is trying to decrease the length, equals to ya delta L by L, and you will get the correct answer for sure. So let's say if they give me on the right end there is a force of 3F towards right, on the left end there is a force of 5F towards left, then what to do? Beta, again take the average. You will write 3F plus 5F by 2, which is 4F, equals to ya delta L by L. So easy. And let's take one more example. If you have got a force of 6F trying to increase the length, while a force of 4F tries to decrease the length, then sir, what to do? Again take the average, but to understand 6F is trying to increase the length while 4F is trying to decrease the length. So you should write 6F minus 4F by 2 equals to ya delta L by L. You will get the answer from here for sure. Okay, so just remember you can use the average of force. So now let's do two examples to understand the difference between shear stress and tensile stress. So the first one, you have a cuboid of length L, width B, height h, and at the top surface we have applied a force F at some angle theta with the surface. Question is, determine the shear stress and the tensile stress due to the force F. To produce shear stress, the force should act parallel to the surface. To produce the longitudinal stress, the force should act perpendicular to the surface, but here the force acts at some angle theta. So what to do? So take the component of force. You can break down this force into component along the surface f cos theta and component perpendicular to the surface, which will be f sin theta. Here you can see f cos theta is trying to move it layer over layer. So what will be the value of shear stress? You will say, sir, shear stress has to be nothing but the force which is trying to move it layer over layer upon the area which moves, and the area which moves in this case is nothing but length into the width, that will be LB. So you will say the shear stress equals to f cos theta by LB. Now what will be the longitudinal stress? To be precise, in this case tensile, as it is trying to increase the length. So you will say the tensile stress will be equal to f sin theta by LB. F sin theta is the force perpendicular to the surface area upon the area, which is LB. So this will be the tensile stress. Let's see one more example of the same type to understand. Let's say we have this rod of cross-sectional area A, and there is one particular area marked which makes an angle theta with the length of the rod. And we are applying some force F on the free end. Question is, determine the tensile stress and shear stress on the shaded area. So what is the tensile stress and what is the shear stress on this shaded area? The first thing we need to do is that we need to find this area. So if I call this particular area A dash, which makes an angle theta with the length of the rod, what will be the relationship between A dash and A? So you will say A dash sin theta will be equal to A. The component of this shaded area perpendicular to length will be equal to A. So first thing we can say is A dash sin theta equals to A. Hence we can say A dash has to be equals to A upon sin theta. Once we have got what is this area, now to find what is the tensile stress and what is the shear stress on it, visualize the forces on this shaded area. So on this shaded area, the force is F and the force is along the length of the rod, so the force will also make an angle theta. One can break down this force into components along the area that will create the shear effect and perpendicular to area that will create the longitudinal effect. So once we break down this force, we get the force along the surface to be F cos theta and the force perpendicular to this area to be F sin theta. Now F sin theta produces the longitudinal effect while F cos theta produces the shear effect. So we can say the shear stress will be equals to F cos theta upon A dash, the area which it is trying to move. Now A dash can be written as A by sin theta. So you can write shear stress to be F cos theta upon A by sin theta, and this sin theta moves from denominator to the numerator. So you will get F cos theta sin theta by A. Similarly, if you need to write the longitudinal stress on this shaded area equals to A dash, you will say that the tensile stress, because it is trying to pull it, not compress it, tensile stress will be equal to F sin theta upon A dash, and in place of A dash you can write A by sin theta. So you get F sin theta upon A by sin theta. So sin theta moves from denominator to the numerator, so you get sin theta into sin theta in the numerator, and that becomes F by A sin square theta. Okay, let's move on. So now we will talk about braking stress. This is an important article, small article. Sir, what is braking stress? The stress at which the object brakes. So that particular stress is called the braking stress, the stress at which the object brakes. Now let's say we have this rod of cross-sectional area A and we need to apply a force F to brake it. If the minimum force required to brake it is F, you will say that the braking stress, for which I am using a simple B, equals to F upon A. Isn't this obvious that if you will have another rod made up of same material but of more radius, having more cross-sectional area, let's say A dash, then the force required to brake it will be higher? So depending upon the cross-sectional area, the greater the cross-sectional area, the more is the force required. What remains same is the stress. The force per unit area required to brake the object remains the same, and that's what makes it important. So braking stress is the stress required to brake the object. Remember that braking stress is an intensive property of material. It does not depend upon the length, the shape, the size. It depends upon the type of material. So breaking stress is independent of length, force and cross-sectional area. For a greater cross-sectional area, you will have to apply more force. For a small cross-sectional area, you will have to apply less force. For what remains same is the breaking stress of the material. So breaking stress do not depend upon the force applied to break, not depend upon the area. Breaking stress is an intensive property. It depends upon the type of material. So if we have a rod of cross-sectional area A and the force required to break is F, then what will be the force required to break a rod of cross-sectional area A by 2 made up of same material? So you will say, sir, the breaking stress remains the same. Let's say here we need to apply a force F dash. The breaking stress for both the rods will be same if they are made up of same material. So you will say F by A has to be equals to F dash upon A by 2. So the 2 moves from denominator to the numerator. So the AA get cancelled and you get F dash equals to F by 2. So as to break a wire of half the cross-sectional area, you will have to apply half the force. Similarly, so as to break a wire of double the cross-sectional area, you will have to apply double the force. Notice that the force changes, the cross-sectional area changes. What remains the same in all three cases is the breaking stress. So breaking stress is an intensive property of material. It is independent of force, cross-sectional area and length. It just depends upon the type of material. That's why this small property is really important. So a simple question. There is a wire of length m, radius r and another wire made up of same material having length L by 2 and radius r by 2. The question goes like, if the wire on the left can support a maximum mass m, then what is the maximum load that can be supported by the wire on the right made up of the same material? So we know that breaking stress is an intensive property. It is not at all dependent upon the length of the wire, the radius of the wire. It depends upon the material. As both are made up of same material, both the wires will have same breaking stress. If the first wire can support a maximum mass m, then the maximum weight it can support is mg. So the maximum stress it can sustain is mg, the weight divided by pi r square. Now let's say the maximum mass that can be suspended for second one is say m dash. So how to write the equation? You will say, assume the maximum mass m dash can be supported from the second wire. The breaking stress has to be same because they are made up of same material. So you will say mg upon pi r square, the stress developed in the first wire, equals to m dash g upon pi r by 2 whole square. Now beta, you can cancel out g, pi, r square. So you will get m equals to m dash upon 1 by 2 whole square. That will be m dash upon 1 by 4, and this 4 moves from denominator to the numerator. So you get m equals to 4 m dash, or m dash equals to m by 4. So m dash equals to m by 4. Or you can simply say, sir, the second wire has half the radius. If it has half the radius, it will have 1/4 the cross-sectional area. If it has 1/4 the cross-sectional area, the force required to break will be 1/4. So the weight of the mass has to be 1/4. So the mass suspended has to be 1/4, hence m by 4. Let's see the next example. Question goes like, determine the maximum length of a wire of density rho that can sustain its own weight given that the breaking stress is B. So this wire is made up of material of density rho. Question is, what can be the maximum length of this wire so that it can sustain its own weight? Why they are asking me this type of question? Because sir, as the length of the wire will increase, visualize a longer wire, then the mass of the wire will increase. If the mass of the wire will increase, then the tension at the topmost point will increase. If the stress at the topmost point became more than the breaking stress, then the wire will break. If we don't want this wire to break, then the stress at the highest point should be less than the breaking stress. So, if we assume this wire to have a maximum possible length L made up of material of cross-sectional area A, then the stress at the top should be less than the breaking stress. So, assuming the cross-sectional area of the wire to be A and the maximum length that can be supported to be L, we know that the tension at the highest point will be equals to mass of the whole wire into G. And you can write the mass of the whole wire same as density into volume. So the density is rho and the volume of the wire is cross-sectional area into L. This becomes the mass of the whole wire. Into G becomes the weight of the whole wire. The weight of the whole wire divided by the cross-sectional area will be the stress at the top. So you will say the stress will be highest at the point of suspension, at the topmost point. As this stress can be maximum equal to breaking stress. If the stress at the highest point became more than the breaking stress, it will break. Just equate the stress at the highest point for this wire of maximum possible length equal to breaking stress. So what will be this stress? Easy. You will write this stress to be equal to mg, the mass of the whole wire, into G upon A. Now that will be equal to breaking stress. Now in place of m, you can write density into cross-sectional area into length into G, and the A get cancelled, equals to B. So the maximum possible length that can be suspended comes out to be equals to the breaking stress upon this rho, and G goes down and the A get cancelled. So B by rho G. This can be the maximum possible length of the wire that can sustain its own weight. Moving on. Now we will talk about something called angle of twist. If you take a wire, fix the topmost point and twist to the lowest end, we say we get an angle of twist. What is the meaning of it? Let's see. So if we have a wire suspended at the topmost point, the top part of the wire is fixed. Let's say this wire has a radius r and a length L. If we turn the lower angle by an angle theta, keeping the top layer fixed, we say that an angle of twist is created. Do not think that this angle of twist is the angle theta by which the wire has been twisted. The angle of twist is the angle which represents the shear strain. Just like in the case of cuboid, a taut, if a force is applied at the topmost point, keeping the lowest one fixed, we know that the shape of this cuboid changes, giving us an angle theta, which for small value of theta represents the shear strain. So what is the angle of twist? The distance moved by lowest layer with respect to top layer upon the length between them. So visualize this. Lowest layer is turned by angle theta. So the points on the perimeter will move a distance equals to r theta. And if the length of the wire is L, then the angle of twist represented by phi can be written as r theta by L. So we say the angle of twist phi will be nothing but r theta by L. So what is r? The radius of the wire. What is theta? The angle by which the lowest layer is turned. What is L? The separation between the top layer and the lowest layer. So the angle of twist phi equals to r theta by L. This is the basic thing you should know. The greater the torque applied to turn it, the greater is the angle theta. The more the torque you apply to turn it, the more will be the angle theta, and hence the more will be the angle of twist, as the angle of twist is directly proportional to theta. So this is all you need to know in the article of angle of twist. Moving on. Now let's talk about bulk modulus. While teaching you bulk modulus, I said that bulk modulus equals to volumetric stress, yes, upon volumetric strain, yes. But I said here that there is a catch here. The catch is that we place a minus sign. Why do we place a minus sign? Let's see. So we know that bulk modulus equals to minus delta P upon delta V by V. Sir, what is delta P? The volumetric stress. You need to change the pressure for volumetric strain. And what is delta V by V? The volumetric strain. And we have placed a minus sign. Why does the minus sign? Because beta, if the pressure of the surrounding increases, you will say that delta P is positive. Yes, sir. If the pressure of the surrounding increases, the delta P is positive, the body placed in this fluid shrinks. So the volume of this body decreases. As the volume of this body decreases, you will say delta V is negative. So beta, if delta P is positive, delta V is negative. So we have to place a minus sign so as to keep the quantity bulk modulus as positive. Similarly, if the delta P is negative, the surrounding pressure decreases, the body swells up. So delta V comes out to be positive. Hence again, to keep the bulk modulus positive, we have placed a minus sign. So bulk modulus equals to minus delta P upon delta V by V. In the differential format, we write the same bulk modulus as minus dP upon dV by V. In place of delta, I have written D. Now, the negative sign here is kept to keep the bulk modulus positive. Now, there is a quantity called compressibility. Sir, what is compressibility? Simply remember, compressibility denoted by K is the reciprocal of bulk modulus. Just like conductivity is the reciprocal of resistivity, compressibility is the reciprocal of bulk modulus. So what is compressibility? Nothing but reciprocal of bulk modulus. So compressibility equals to 1 by bulk modulus. So K equals to 1 by P. Now if we have a gas undergoing polytropic process, PV raised to the power of x equals to constant. I have just taught you in the hour of thermodynamics, polytropic process, and there I have specified on this point. If we have a gas following a polytropic process, PV raised to the power of x equals to constant, then the bulk modulus for this gas is given by xp, the polytropic coefficient times the pressure. So if a gas undergoes a polytropic process, PV raised to the power of x equals to constant, then the bulk modulus of this gas is the polytropic coefficient times the pressure. Now, for a given mass of substance, we can write mass equals to density into volume. For small changes, we can write delta m by m equals to delta rho by rho plus delta v by v. Usually, when the body expands or shrinks, its mass does not change. So you can write 0 equals to delta rho by rho plus delta v by v. What is delta rho by rho? Sir, fractional change in density of the body. What is delta V by V? The fractional change in volume of the body. Now, in bulk modulus, we write bulk modulus to be minus delta P upon delta V by V. What is this delta V by V? The fractional change in volume of the body around which the pressure has been changed. So now here, we can even write delta V by V equals to minus delta rho by rho. If here, in place of delta V by V, we substitute minus delta rho by rho, then beta this 2 minus will get cancelled and you will get bulk modulus equals to delta P upon delta rho by rho. So one can even write bulk modulus in terms of density as delta P upon delta rho by rho, delta P upon delta rho by rho, or even in differential format as dP upon d rho by rho. So this is another method to use bulk modulus when they ask you to talk in terms of density rather than fractional volume change. Let's move on. So now let's talk about Poisson's ratio. Poisson's ratio denoted by the symbol sigma. If we have a rod of length L and having a radius R, if we are applying forces at both the end of the rod to elongate it, what happens? Sir, the length of the rod increases. So obvious, but what happens to the radius? If you visualize a rubber band and you pull it, the length increases, no doubt. What happens to the radius? Sir, the radius decreases. So on stretching, the length increases and changes from L to say L plus delta L, while the radius decreases and changes from let's say R to R minus delta R. So the length increases while the radius of the wire decreases. Here we say two types of strains are created. There is something called longitudinal strain. The longitudinal strain created will be equals to delta L by L. And there will be also a lateral strain. The lateral strain will be equals to the change in radius upon the original radius. Isn't it obvious if the length increases, the radius will decrease? So if delta L will be positive, then delta R will be negative. And if you compress the rod, the length decreases, so the delta L will be negative. And when you compress the rod, it becomes thicker, so the delta R, the radius will increase and delta R will be positive. So the lateral strain and longitudinal strain have got opposite signs. The lateral strain and longitudinal strain have got opposite sign. Hence we define Poisson's ratio as minus times the lateral strain upon longitudinal strain. Again the minus sign for the same reason why we placed it in bulk modulus, to keep the ratio positive. So as to keep the Poisson's ratio positive, we have placed a minus sign. What is Poisson's ratio? Minus times the lateral strain upon longitudinal strain. What is lateral strain? Change in radius upon radius. What is longitudinal strain? Change in length upon length. So sigma equals to minus delta R by R upon delta L by L. Now, negative sign is kept to keep sigma positive. Keep this small thing in mind. Now, there is one special case for which Poisson's ratio is asked many a time that you should know. If we have a wire which on stretching stretches in such a way that its volume remains constant, then what is the Poisson's ratio for such a material? So you will say, for the wire of constant volume which on stretching stretches in such a way that its volume remains constant, what will be the Poisson's ratio for such a wire? That is the question. So for a wire of constant volume, we can write the volume of the wire to be equals to pi r square L. Using the small change approximation, we can say that delta V by V equals to 2 delta R by R plus delta L by L. We are solving for the special case when there is no change in volume. So the fractional change in volume has to be 0. So you will write 0 equals to 2 delta R by R plus delta L by L. Now you can bring this term of 2 delta R by R on the left hand side and divide it with delta L by L. So you will get minus 2 delta R by R equals to delta L by L, or minus 2 delta R by R upon delta L by L equals to 1. If you bring this 2 to the right hand side, you will get delta R by R upon delta L by L, and there is a minus sign, equals to half. Now when you get minus delta R by R upon delta L by L equals to half, you can say that Poisson's ratio equals to half. So for a wire which elongates in such a way that its volume remains constant, we can say that the Poisson's ratio is half or 0.5 if the volume of this wire remains constant. So this is an FAQ, you should remember it. So now let's talk about the three formulas. Which three formulas? The three formulas correlating Young's modulus with modulus of rigidity, bulk modulus, and the Poisson's ratio. The first formula goes like Young's modulus equals to 2 times the modulus of rigidity multiplied by 1 plus Poisson's ratio. The second formula is Young's modulus equals to 3 times the bulk modulus times 1 minus 2 sigma. And the third formula, 9 by Young's modulus equals to 3 by modulus of rigidity plus 1 by beta. The question which came in this year mains paper was based on the third formula. So how to remember these three? Beta, I have made up a little bit of trick. Remember that on the left hand side you always get Young's modulus. On the left hand side we are getting Young's modulus. On the right hand side 2 neta, 1 plus 1 sigma. Okay, so sigma gets added to 1 plus sigma. Moreover, this first formula is utilized to tell that Young's modulus is greater than the modulus of rigidity. Why? Because it is 2 times the modulus of rigidity multiplied by something positive. So it is more than the modulus of rigidity. So from the first equation we can say that Young's modulus is greater than the modulus of rigidity. Second thing beta, for bulk modulus, bulk modulus, bulk, 3-dimensional forces act. That's why there is a 3 in the case of bulk modulus times 1 minus 2 sigma. Here you have added, so here you should subtract. Here you had 2 and 1. Here you have 3 and 2. So memorize it simultaneously, all 3. The third one I memorized at 9, 3, 1. 9 divided by 3, 3 divided by 1. 9, 3, 1. Yes, no, baby. So 9, 3, 1. Yes, no, baby. So 9 by Young's modulus equals to 3 by modulus of rigidity plus 1 by the bulk modulus. 9, 3, 1, yes, no, baby. So I will recommend you to remember all 3 simultaneously if you are remembering. And from the first equation, we can say that the magnitude of Young's modulus has to be more than the magnitude of modulus of rigidity. So moving on. So now let's talk about stress strain curve. If we have a wire connected to a pan on which we can change the mass. By changing the mass, we can change the tension in this string. By changing the tension in the string, we can change the stress in the string. And we have placed a scale with the wire to measure how much the wire has elongated. Once we know what is the elongation in the wire, when we create a particular amount of stress, we can find what is the strain, because the strain will be equal to the change in length upon the original length. If we plot a graph of stress strain utilizing the different value of stress and the different amount of strain generated in the wire, we get a curve which looks something like this. You can notice that in this curve, for the initial part, we get a straight line. Why do we get the straight line? From the Hooke's law. For small value of stress, the strain is directly proportional to stress. Now let's say the initial part, the straight line, makes an angle theta with the strain axis. What will be this angle theta? So you will say tan theta will be equals to stress upon strain, the y-axis upon x-axis. Tan theta will be equals to stress upon strain, and stress upon strain represents the Young's modulus. So if they give you a case where they give you the stress strain graph within the proportional limit and give you two material 1, material 2, they might ask you which material has got higher Young's modulus. So the material 2 has got higher value of theta. Since the material 2 has got higher value of theta, the value of tan theta for material 2 will be higher. Hence, the Young's modulus for material 2 will be higher. But be cautious in paper. They many a time flip the axis, and rather than giving the stress on the y-axis, they give strain on the y-axis while giving the stress on the x-axis. If they do this, then the answer reverses, because now you have to measure the angle with the strain axis again, and now one has got more angle, so one has got higher value of Young's modulus if they flip the axis. So tan theta represents the Young's modulus. Now let's understand different important terms related with this stress strain curve. There is a particular point A on the curve which is called proportional limit. Think how intelligent name. Proportional limit. What is the meaning of proportional limit? The meaning of proportional limit is that the point on the curve up to which stress is directly proportional to strain. The point on the curve up to which Hooke's law is valid, that represents proportional limit. If you keep on increasing stress up to a particular limit, they are directly proportional. And then on further increasing it, the Hooke's law is no more valid, and we find that the curve bends. Now let's say there is another point on this curve. This point is point B. The name of the point B is elastic limit. Elastic limit. The limit of strain up to which the material is elastic is called elastic limit. Now, what is the meaning of elastic limit? If the strain is up to this point B, then on unloading the mass, on removing the mass, the wire completely regains its original shape. It completely regains its original length. If the strain becomes more than this, then even on unloading the mass, the wire won't regain its complete shape. Now, if the strain becomes more than at point B, let's say up to here, then even on unloading the mass, the wire do not regain its complete shape, and when you remove the mass, make the stress drop to 0, even then some strain persists. This strain that persists even when now you make the stress equals to 0 is called permanent set. If the strain has crossed the elastic limit, then on unloading the mass, on making the stress 0, even some strain persists, and this strain that persists is called permanent set. Now let's talk about next point. There is a point C, which is the peak of this graph. You can see once you reach the point C, then to increase the strain, you do not have to further increase the stress. This point C, at which the strain keeps on increasing without further increase in stress, is called the yield point. In the NCERT, the definition of yield point is given to be same as the breaking stress, which is not correct. But a yield point is the place where the strain keeps on increasing even without further increase in the stress. Now, if you keep on elongating, if you let it elongate, then at a particular point it breaks, and this point is called the fracture point. So these are the data you must know about the stress strain curve. Moving on, we need to understand the loading unloading curve. What is the meaning of loading unloading curve? If you first increase the mass in the pan and then start to decrease it, what type of curves do we get? So the standard loading unloading curve when you increase the strain within the elastic limit, it means that the body completely regains its shape on complete unloading. We get this type of curve. While loading, we get one curve, and while unloading, we get another curve. But since the strain has not crossed the elastic limit, that's why the body completely regains its shape, and when the stress drops to zero, the strain also drops to zero. So this is the standard loading unloading curve. This is also called hysteresis curve. Why? Because on increasing the stress, the strain increases. But when you decrease the stress, the strain do not decrease following the same path. It decreases using an alternate path. Moving on. If the material we are using is perfectly elastic material, elastic collisions are the one in which there is no energy loss, then the loading and unloading curve are same. So the unloading curve is exact on the same lines as of loading curve, given that it is a perfectly elastic material. Because beta, the area enclosed by the loading unloading curve represents the energy loss. You will learn the same thing in magnetism. The area enclosed by the hysteresis graph is directly proportional to the energy loss. Now, if the stress goes beyond the elastic limit, if you have increased it so much that you have crossed the elastic limit, the initial part of curve, then on loading the stress increases, strain increases, but you have crossed the elastic limit, then on unloading you know that the final strain won't be zero, there will be some permanent set. So this is what the unloading curve looks like. Remember that the area enclosed in this loading unloading curve is directly proportional to the loss of energy. If your material is perfectly elastic, then there has to be no loss of energy. That's why I see here there is no area enclosed. Moving on, let's talk about elastic potential energy. So if you have a spring and you apply a force, you know that the force is directly proportional to the deformation in the spring, and you know that F equals to kx. Now, if you have a rod and you apply a force, I said that this case can also be correlated with the case of spring. So here also we know that the force is directly proportional to the deformation, F equals to YA delta L by L, and I told you guys to take this YA by L as a proportionality constant K. So F, which is equals to YA delta L by L, is directly proportional to L. Hence, you can treat YA by L as the spring constant K. Now, for a spring, the potential energy stored in the spring when it has a deformation X is given by half kx square. Similarly, if you have a rod in which an elongation delta L is produced, you can write the elastic potential energy stored in the rod to be half into the constant for this rod, which is YA by L into delta L whole square. So half into YA by L into delta L whole square. Personally, when I start solving a question based on elastic potential energy of a rod, I start solving using this particular formula, half into YA by L into delta L whole square. But you can play more with it. You will write elastic potential energy stored in the rod equals to half into YA by L, and rather than writing delta L whole square, write delta L into delta L. Now you can write this YA delta L by L part as the force responsible for making this elongation. So you will get the elastic potential energy of the rod is half into force into delta L. Now beta, multiply and divide with the volume of this rod, cross-sectional area into length. So when you multiply and divide, you can move this A under the force, this L under the delta L, and this whole AL under the elastic potential energy of rod. So you will write the elastic potential energy of rod per unit volume divided by AL equals to half into F by A into delta L by L. Why are we doing this? So that we get elastic potential energy per unit volume equals to half into force per unit area, stress, into delta L by L, which is strain. So the elastic potential energy stored in the rod per unit volume is nothing but half into stress into strain. Half into stress into strain. Okay. So remember that this particular elastic potential energy per unit volume, which is also called energy density, energy per unit volume, can also be written as rather than half into stress into strain. In place of stress, you can write Young's modulus into strain. Sir, how? Beta, Young's modulus equals to stress upon strain. So stress can be written as Young's modulus into strain. If in place of stress you substitute Young's modulus into strain, you get half into Young's modulus into strain into strain. So that gives you half into Young's modulus into strain square. Or in place of strain, you can write using Young's modulus equals to stress upon strain. In place of strain, you can write stress by Young's modulus. So what you get is half into stress by Young's modulus. So that gives you half into stress square by Young's modulus. So what I personally recommend students to remember is this: the elastic potential energy stored is just like half k x square. In place of k, you have to write y a by L, and in place of x, the deformation, you have to write delta L whole square. And I tell them to remember this very, very carefully. The energy density, energy stored per unit volume of rod equals to half into stress into strain. So remember both of them. Moving on to the last heading, which is the sagging of beam. If we have a beam of weight W, length L, width B and height D, suspended between two supports, over the period of time, this beam sags. Now let's say this beam sag by an amount delta. What is this delta equal to? So delta equals to WL cube by 4YB D cube. So what is W? The weight of the beam. What is L? The length of the beam. So if the length of the beam becomes double, keeping everything else same, the sagging becomes 8 times, because the sagging is directly proportional to L cube. In denominator, you have got Young's modulus. The greater the Young's modulus, the less is the sagging. The greater the Young's modulus, the harder the substance is, the less is the sagging. The greater the width, the less is the sagging. And the greater the height, the less is the sagging. Okay, so the more the height of the beam, the less is the sagging in the beam. Now this is the question asked. If you make B double, then the sagging becomes dash times. So if width becomes double, here B becomes double, the sagging becomes half, because sagging is inversely proportional to B. But if the height of the beam becomes double, so in place of a beam of height D, you have got another beam of height 2D. If the height of the beam becomes double, then what happens to sagging? If the height of the beam becomes double, then delta is proportional to 1 by D cube. When the height of the beam becomes double, the sagging becomes 1/8. That's why to reduce the sagging of a beam, it is better to increase D rather than B. Because when B becomes double, the width becomes double, the sagging becomes half. But when the D becomes double, the height of the beam becomes double, the sagging becomes 1/8. So that's all in some mechanical property. In the next hour, we will talk about fluids, and the first one will be fluid statics. See you guys. Bye-bye. So that's all for now. See you guys in the next hour.